Coin cells are a valuable starting point for energy research because they offer a simple, fast, and cost-effective way to evaluate new materials and chemistries. Their small size and straightforward assembly make them ideal for early-stage experiments, enabling rapid iteration and comparison between samples. Hi, I'm Georgia from PI-KEM, and today we're going to walk you through the fabrication process for coin cells. Whether you're developing lithium-ion, sodium-ion, or next-generation solid-state systems, coin cells allow researchers to quickly screen electrode formulations, test electrolyte compatibility, and verify new concepts before moving forward to more complex cell formats. The performance of a coin cell is highly dependent on the cell's fabrication quality. Creating a high-quality coin cell requires precision, attention to detail, and proper technique. From mixing the perfect slurry to crimping the final cell, in this video we'll cover the essential techniques, walking you through the process of how to create a perfect coin cell. The coin cell fabrication process comprises 5 key stages: electrode slurry preparation, coating and drying, calendaring, precision electrode cutting, and final cell assembly through crimping. Let's begin with the anode and cathode slurries, the active foundation of a coin cell. Electrode slurry preparation is an important first step, where we mix the anode and cathode materials with a binder, conductive additives, and a solvent. The exact composition of your electrode slurry will be dependent on your specific cell chemistry. We begin with mechanical grinding, breaking down hard agglomerates to achieve a uniform powder with no visible lumps. For this demonstration, we are going to be using chalk powder. Next, we add our solvent. It's important that you add your solvent gradually and in the correct ratio. The amount of solvent you add will determine your slurry's viscosity and coating behaviour. Here, we are using water as a solvent, but your solvent will depend on your anode and cathode materials. The powder and solvent should be mixed uniformly. Thorough mixing ensures complete particle wetting. The goal is a smooth, homogeneous slurry with no lumps or inconsistencies. The next stage is electrode coating, where we transform our slurry into a functional electrode. Electrode coating can be done with a flatbed coater. The coating process must achieve uniform thickness, consistent material loading, minimal defects, and strong adhesion to the metal foil. For cathode materials, we typically use aluminium foil, and for anode materials, copper foil is used. For this demonstration, we will be using paper. The doctor blade consists of a straight blade positioned above a substrate. The gap between the blade and the substrate determines the thickness of the wet film that is deposited as the blade moves across the surface. Adjustable micrometer screws allow precise tuning of the blade to foil distance. Increasing the gap results in a thicker deposited film, while decreasing the gap produces a thinner film. When securing the foil onto the coater bed, the foil must be completely flat. Using the vacuum feature or temporary adhesive tabs ensures the substrate remains stationary during coating. Pour your slurry ahead of the doctor blade with enough volume to cover the full length of the foil. Here, we are using gouache paint to demonstrate. Adjust the speed at which the doctor blade will move over the foil and set the distance along the foil that it will travel. The doctor blade moves across the foil, leaving behind a smooth and consistent layer of slurry. The goal is a layer of uniform slurry thickness across the foil surface. Coating speed influences how evenly the slurry spreads across the electrode foil and how clean the coating edges are. Slurry viscosity is also an important variable for coating thickness. Viscosimeters can be used for consistency and repeatability between cell batches. Some slurries can be left to air dry, however some coaters feature top-down, bottom-up or two-directional heating elements to assist in solvent evaporation. After coating the slurry onto the electrode foil and allowing it to dry, the next step is calendaring. This stage helps to improve the overall electrode performance. Calendaring is a mechanical compression process where we pass the dried electrode through precision rollers to densify it. This step influences electrode uniformity, thickness, porosity, and energy density. The key parameter for calendaring is the roller gap, which determines how much compression is applied to the coated electrode foil. The gap should be set based on your target electrode thickness and density. Feed your dried electrode into the rollers smoothly and evenly, keeping tension consistent to prevent wrinkles. The electrode should enter straight and flat. In this demonstration, we're using cold calendaring, which is compression at room temperature. The alternative is hot calendaring, which uses heated rollers. The optimal approach will depend on your specific coating formulation. After drying and calendaring, we need to cut our coated electrode into precise discs that fit within the coin cell. The cutting process must create clean edges without damaging the coating or deforming the metal foil. When cutting your electrode discs, consistent spacing between cuts can help to minimize waste, allowing you to cut the most electrodes from each coated foil sheet. Applying firm pressure to the disc cutter creates a clean cut without damaging the coating or the foil. Handle cut electrodes only by the edges, using clean tweezers to avoid damaging the surface, creasing the electrode, or transferring oils, dirt, or moisture that may affect the cell performance. We now arrive at the final stage, cell assembly and crimping. All of the components are stacked together into a cell case, and then crimping seals the cell and ensures all the internal components are properly compressed and aligned. Stacking the cell components in the right order with the correct electrode orientation is vital to ensuring cell operation. The anode disc is placed coating side up. Next, add your separator, ensuring it is centered and completely covers the anode. Now the cathode disc coated side down. This configuration ensures both active electrode surfaces are in direct contact with the separator. Add the spacer and then the spring. In a functional cell, liquid electrolyte would now be injected. For this demonstration, we are only performing the component stacking. Finally, manually secure the top cap and squeeze everything together. Position your assembled cell carefully in the crimping die cavity. The die is designed to compress the case evenly all the way around. Close the pressure valve and then pump the handle to increase pressure. For CR2032 cells, we typically use around 1000 psi of pressure. The crimping process forms the case rim to create a tight seal with the cap gasket. Hold briefly at full pressure and then release the valve. To remove the cell, press down on the outer rim of the die and slide the finished cell free. A properly crimped cell shows a smooth, even crimp all around the edge. This is your finished coin cell. It represents careful preparation and attention to detail at every step. Following these steps ensures consistent, high-quality coin cells for your battery research. The completed cell can then be analysed and tested for performance, durability, and safety. Coin cells are where the journey begins. They allow researchers to rapidly test new materials, validate performance targets, and build confidence in their chemistry. But coin cells are only the first step. As projects mature, the focus shifts to scaling, moving into larger cell formats such as pouch cells and ultimately into pilot line production, where process consistency and cost efficiency becomes critical. PI-KEM can provide a complete ecosystem for battery research excellence, from high-purity electrochemicals and cell consumables to precision coating equipment, calendar presses, cutting dies, and crimping systems. We supply researchers and manufacturers with the tools and materials needed for innovation in energy research. Get in touch today to discuss how we can help support your research. And keep an eye out for upcoming videos where we'll take a deeper dive into each stage of the battery manufacturing process.